Thank you for your interest in this paper. Now let's introduce this paper. A simple baseline for video restoration with grouped spatial-temporal shift. Let's begin. First, we will give a 1-minute quick preview. We propose a simple method, named grouped spatial-temporal shift for effectively video restoration. Our method does not require the previous optical flow estimation, deformable convolution or self-attention layers. As shown in the bottom left images, optical flow estimation is not that accurate in blurry images or noisy images. A common idea of optical flow, DCN and self-attention layers is increasing the receptive fields for temporal information alignment. The success of self-attention layers lies on the increasing receptive fields of a single attention layer. Therefore, we extend the simple shift operations to achieve large receptive fields of a single CNN layer. Our method surpasses previous SOTA methods on video deblurring and denoising. From now on, we will provide more details of our method. The first is introduction. The popularity of capturing videos using handheld devices continues to surge. However, these videos often suffer from various types of degradation, including image noise due to low-cost sensors and severe blurs resulting from camera shake or object movement. Consequently, video restoration has garnered significant attention in recent years. The keys of video restoration methods lie in temporal information aggregation. Most methods rely on explicit alignment to establish temporal correspondences, using optical flow or deformable convolution. However, these approaches often necessitate either complex or computation-ally expensive network architectures to achieve large receptive fields, and they may fail in scenarios involving frame noise and blurry regions. A video restoration transformer, VRT, is developed to model long-range dependency, but its large number of self-attention layers make it computationally demanding. While several methods employ convolutional networks for multi-frame fusion without explicit alignment, their performance tends to be suboptimal due to their shallow receptive fields. It's observed that most previous methods resort to large receptive fields for temporal aggregation. There are two naive ideas. The first one is to use large kernel convolutions. However, extremely large kernels are still difficult to optimize in low-level visions. The second one is increasing the shift window size of self-attention, which would increase the computational cost quadratically. By the way, it is shown in the bottom paper that the alignment range of transformers is equal to the shift window size. Inspired the above considerations, our key idea is enlarging the receptive fields in a single CNN layer, which is implemented by the combination of simple shift operations and small kernel convolution. We adopt a 3-stage design. The first and third stage are frame-wise processing. The core of the method is the multi-frame fusion implemented by grouped spatial-temporal shift blocks. The grouped spatial-temporal shift consists of grouped temporal shift and grouped spatial shift. For the grouped temporal shift, we utilize a bidirectional temporal shift. It is observed in our experiment that handling 3 frames at one time is difficult. To avoid this issue, we utilize bidirectional temporal shift to allow the block handle 2 frames at most. For the grouped temporal shift, we slice the features into multiple groups and shift them with different directions and strides. Then a simple fusion layer fuses the spatial temporal shifted features. For the implementation of fusion layer and the receptive fields details, please refer to our paper and GitHub page. In our experiments, we compare our method with SOTA video deblurring methods on GoPro dataset. It is shown that our method surpasses previous methods with a large margin.
Then we provide comparisons of video denoising on Davis dataset. It is shown that our method could recover more details than other methods. In ablation study, we compare our shift blocks with self-attention layers, deformable convolution and optical flow. It is shown that the combination of convolution and shift operations achieves better performance with less computational cost. We further analyze the influence of optical flow on different tasks. We remove the optical flow from basic VSR++ for different tasks and increase the other computations for fair comparisons. It is shown in right table that the optical flow does improve the video super resolution greatly. BU cannot help in deblurring and denoising. The left visualization also shows that the optical flow are inaccurate due to blur and noise. In conclusion, our contributions are in the following. 1. We extend shift operations to achieve larger receptive fields. 2. We propose a simple, yet effective framework for effective temporal feature aggregation for video restoration. 3. Our framework surpass state-of-the-art methods with much fewer flops on video deblurring and video denoising. 4. We show optical flow has different influences on different tasks. Optical flow can help video SR, but cannot help much in video deblurring or denoising, which may inspire further explorations.
Thank you for listening. For more details, please refer to the paper and GitHub code.